Hi, welcome back to my class. We'll continue with the topic from the last class, which we have discussed about the Coulomb's law in vector form, about electric field, and then little bit about the electric field lines. So we were dealing with the electric field lines. Electric field lines. So these are the lines which represent the strength of the electric field. So if you have any positive charge, field lines are directed outwards, and if it is negative charge minus Q, field lines are directed towards itself. So this is how we represent the electric field lines. Okay. Now there are some properties of electric field lines. First one is that they do not form any closed loop. Electric field lines will never form closed loop. Okay. And next one is two or more electric field lines will never cross each other. So what will happen if they cross each other? If they cross at the point of intersection, it will have two directions, which is not true. Correct? If I have a positive charge, field lines are outwards. If it is a negative charge, field lines are towards itself. So at one particular point, it will show only one direction. So that's why two or more electric field lines will never cross each other. Same way how you have already studied in 10th standard regarding properties of magnetic field lines. Magnetic field lines will never cross. In the same way, field lines, electric field lines will also not cross each other. So this is one more thing. Another thing is, if you have any point charge, then electric field lines will start or end at infinity. So if you consider point charge, they will start or end at infinity. Point charge or single charge if we have. So these are some of the properties of electric field lines. Next we will move on with the electric flux. Brief introduction I have already given regarding this flux. What do you mean by flux? So if you have any closed surface, or if I consider a cone shape this way, if I have considered like this, so then what about the electric field lines? So these are the field lines. So if you want to define electric flux, so those are the field lines or relative density, number of field lines crossing per unit area of cross section. Okay. Now how will I represent that? So if I have any, say that I have electric field like this. Okay. So this is the direction of the electric field. I want to find the electric flux at this point. So what I have to do is, you place one plane perpendicular to the direction of the electric field like this. Now what you have to do? Calculate the cross-sectional area and calculate the number of field lines crossing through that required cross-sectional area. So dot product of that will give you the electric flux. So flux is represented as phi. Phi can be written as E dot delta S or ds. What is this delta S or ds? It is a small surface area where you are considering the electric field lines to pass through. I hope it is clear. So phi or electric flux is nothing but E dot delta S. Delta S vector weighted. Now if the cross-sectional area what you place is like this, then what you have to consider? You have to consider the angle between that. Okay, like this, you have to resolve that into components and find out this component. Usually it is cos theta component, correct? Why? Because along that line if you are resolving, it is cos component, the other one will be the sine component. So we will be considering this only, so cos component. So if it is placed like this, then you have to consider the cos component. Okay, so it is a vector notation. So flux phi is equal to E dot ds. Now what will be the SI unit of electric flux? Can you just think? E, how can I write E? F by Q, correct? Into delta S. Delta S is nothing but area. So now Newton per coulomb meter square. This is very important. So this is the SI unit of electric flux. Force Newton by Q, that is per coulomb. Delta S is area, which we usually represent as meter square. So it is Newton per coulomb meter square is the SI unit of electric flux. Moving into the next topic, dipole or electric dipole. Again, very important topic. We have two derivations under this, but it is simple. Only the calculations we have to do, simplification. So before that, we will go with the definition. Basic idea about the dipole. As the name indicates, di means two. It will have two poles or two charges. So I will be writing as plus q and minus q, which is separated by a distance of 2a. This whole system is called as electric dipole. We are dealing with the charges. So plus q and minus q, equal and opposite charges which are separated by a distance of 2a is called as dipole or electric dipole. Now here two points you have to keep in mind, that is net charge. What will be the net charge? Will always be 0, but net electric field will not be 0. Okay? Net electric charge will be 0, but net electric field is not 0 in the dipole. Somewhere here in the middle, if you consider, there will be minute amount of electric field. Okay, so net charge will be 0, net electric field will not be 0. Now, the line joining these plus q and minus q will have one center. So this is called a center of dipole. That is not a definition as such, but you have to know that one, that point. Okay, so it is a separation of 2a, distance is 2a. But somewhere if you consider any point outside this region which is very much greater than 2a, then you can consider that net electric field will be 0. There will not be any effect of these two charges. If you consider any point which is very far from this 2a, or if that particular distance is very far from this 2a, so it is written as r is very much greater than 2a, then electric field can be considered as 0. But in our discussion we consider this very smaller distance for some concepts. So in that case, please don't consider electric field as 0. Okay. Now here you have two derivations. First one is how to calculate the electric dipole on its axis. Now what do you mean by axis? This one. The line joining these two charges is called as an axis. Okay. So if you want to find out the electric field somewhere here or here or here, then you have to consider this line. So how are we going to derive the equation? That we will study. Sorry. Next one will be about the equatorial plane. How to find out the electric field at any point in the equatorial plane. Now what is that equatorial plane? It is any plane which is perpendicular to this axis. If I have like this, if I want to find out the electric field here, so it is like this, perpendicular to this axis. So this plane if I want to consider, so then how to deal with that concept. Okay, so these are the 2 points which we are going to study in today's class. So that is very important. So 2 simple and small derivations which we are going to study. Okay, so please keep in mind electric dipole, 2 two equal and opposite charges which are separated by a distance of 2a. Okay. And we will also see how the electric field reduces as you go away from the charges. Whether it is inversely proportional to R, whether it is inversely proportional to R square or inversely proportional to R cube, we will see. Okay. So first derivation. Electric field due to a dipole. Consider the two charges plus q and minus q which are separated by a distance of 2a. One more thing, please note that the direction of electric field in a dipole is always considered from minus q to plus q. This direction is considered universally, okay, minus q to plus q. That we will represent as P, which we will discuss later, called as dipole moment. So once I discuss this derivation, that time I will explain the concept of dipole moment, which is always represented from minus q to plus q. So now I will represent it this way. So it is P, okay, minus q to plus q. If I consider this point, so from here to here it is A, again from here to here it is A, midpoint of the line joining the two charges. If you represent the diagram very neatly, then the derivation becomes very simple. And note that the representation of diagram is very, very important as an examination point of view also. It carries mark. Okay. Please draw it neatly, use pencil, scale and draw it properly. Now, I want to find out the electric field at this point P, which is at a distance of R from the center. How will I find this? Total electric field due to these two charges. Now, due to plus Q, direction will be like this, E plus Q I will write at this point. And due to minus q, it will be like this, E minus q. Because minus means it is always attracted, plus means it is always away from here. So I will represent like this. So let us start the derivation. E due to plus q, electric field. I have to write the equation now. So it is 1 by 4 pi epsilon naught q divided by, from here what is the distance? Total is r minus a whole square. Okay, so total distance is r from this point. So r minus a, we want only this much distance. So what will be this much distance? R minus a whole square. E due to minus q is minus 1 by 4 pi epsilon naught, minus charge, so q divided by, what is the distance of this P, point P from minus q? So R plus A, R plus A whole square, R minus A whole square and R plus A whole square. Now we will find out the total electric field. If you are using the vector notation, then you have to write the unit vector, okay, P. P is the dipole moment that we will discuss next. Now the total electric field. So total electric field E is nothing but E due to plus Q plus E due to minus Q. So add the two equations. So it is 1 by 4 pi epsilon naught q divided by r minus a whole square into p cap plus 1 by 4 pi epsilon naught, sorry, minus, I will write here only, q divided by r minus a, the r plus a the whole square into p cap. So you can take out the common terms outside. 1 by 4 pi epsilon naught q into 1 by r minus a the whole square minus 1 by r plus a the whole square into p cap. So q by 4 pi epsilon naught into cross multiply r plus a the whole square minus r minus a the whole square divided by r square minus a square whole square into p cap. Just take the LCM, expand this one, q divided by 4 pi epsilon naught into r square plus a square, a plus b whole square, a square plus b square plus 2ab. So r square plus a square plus 2ar minus r square minus a square minus and minus plus 2ar divided by r square minus a square the whole square into p cap. So what I have done, I just explain again so that I can erase this much and write the next concept. So plus q, E due to plus q charge and E due to minus q charge. 1 by 4 pi epsilon naught q divided by r minus a whole square and minus q divided by r plus a, r minus a and r plus a, that is from minus q. Then you have to add the two equations and take the common term outside, q by 4 pi epsilon naught. It is a simple mathematics. Take the LCM and here you can see that these two terms will be cancelled. Correct? Now we will simplify this one. So E will be equal to q by 4 pi epsilon naught into 2ar plus 2ar, it is 4ar divided by r square minus a square the whole square into p cap. Now if I consider r very much greater than a, so this r is so much greater than a, then this can be neglected. So what I will get, E is equal to q by 4 pi epsilon naught into, I will write like this, 2 into ar divided by r to the power of 4. Because a is very small, this can be neglected. I will tell why I have written this 2 into 2. Okay. R to the power of 4. So 1 r will be cancelled. So the final equation will be E is equal to q by 4 pi epsilon naught into 2 into 2a divided by r cube into p cap. Now this is there, no? 2a into q, we can call it as dipole moment. Okay, dipole moment. So now just remember like this, q divided by 4 pi epsilon naught. This you just keep in mind. After the second derivation, clubbing together I will explain. Okay, here you can directly write in the examination, you can directly write it as 4a. I have written here just to explain that concept. So it is 4a divided by r cube into p cap. So this is the expression for electric field along the axial line. Electric field in an equatorial plane. So any point in an any point in an equatorial plane, how are we going to find out the electric field? Okay, so again consider the simple diagram. So please see that you draw the diagram very neatly and clearly, okay, which is separated by a distance of 2a. Consider the midpoint, so this will be A and A. Okay, so this is minus, we will consider, plus q and minus q. Two equal and opposite charges form a dipole separated by a distance of 2a. Say that I want to find the electric field at this point, which is in an equatorial plane perpendicular to this line joining the dipole at this point. Okay, say that it is at a distance of r. Now you will have the E plus Q this manner, and this way it is E minus Q. So now this will be the net electric field according to the parallelogram law of vector addition. So one more thing is that based on the Coulomb's law and parallelogram law of vector addition, superposition principle, we can find out the net electric field. Okay, so Coulomb's law and superposition principle are very, very important in order to find out the net electric field. So please note that the direction of the electric field is very important. So it is E minus Q and it is E plus Q. This is the net electric field E. Let me write the equations again. So electric field due to plus Q at this point P. It is 1 by 4 pi epsilon naught Q divided by, I have to find this distance now using the Pythagoras theorem. So it is Q by R square plus A square. This distance R square plus A square whole square, correct, into P cap. I hope it is clear. This distance is from plus Q. Point P is at a distance of square root of R square plus A square. The simple formula, the basic formula is Q by R square. So it is square root of that square. So it becomes the same, correct. Similarly, E minus Q, 1 by 4 pi epsilon naught Q divided by R square plus A square under root whole square into P cap. Now the thing what you have to note down is, in the dipole, the direction of dipole moment is from minus Q to plus Q. Okay, that we are considering. But this net electric field is in the opposite direction. It is in the opposite direction. So now you have to consider the net direction as negative. Okay, negative of this one. So the net electric field E will be equal to minus of E due to plus Q, E due to minus Q cos theta into P cap. Cos component you have to consider. So now substitute the values. 1 by 4 pi epsilon naught Q by R square plus A square plus 1 by 4 pi epsilon naught Q divided by R square plus A square into cos theta. Cos theta into P cap. Later you have to substitute the value of cos theta. So now minus Q by minus in total, because it is opposite to the direction of the dipole moment. So 4 pi epsilon naught 2Q divided by R square plus A square. No need to take any LCM here. Both are the same. Both denominators are same into, sir, Q I have already considered. So 2 we will write. Now cos theta. What is cos theta here? Adjacent by hypotenuse. So A divided by R square plus A square to the power of 1 by 2. Why 1 by 2? It is square root into P cap. Okay. This is A. Now So minus 2qa divided by 4 pi epsilon naught into r square plus a square into r square plus a square whole to the power of half. Total it is 3 by 2. So r square plus a square to the power of 3 by 2 into p cap. Okay. So this one 2qa 2a into q. We can write it as p. Now later we will see that one. If I consider r, same like how we did before, if I consider this r very much greater than a condition, then what I will get? Vector e. This is vector e. Okay. Minus 2a into q divided by 4 pi epsilon naught into r cube into p cap. This a will be cancelled. R square whole to the power of 3 by 2. 2 and 2 will be cancelled. Remaining is r cube. Okay. So see that in both the cases it is inversely proportional to r cube. And it is that it doesn't depend only on plus q and minus q. It depends on r also. Which one? Electric field. Now this one. This E we will write it as minus vector P divided 2A into Q divided by 4 pi epsilon naught into R cube. So this is E equatorial. Okay, this is E equatorial. Minus P divided by 4 pi epsilon naught into R cube. For the axial it was minus 2P. Okay. P into this unit vector will give you the dipole moment. So the product of any one of the charge and the distance separation between the two charges will give you the dipole moment represented as capital P vector. P into P cap will give you vector notation P. Okay. So remember that for equatorial it is just minus P. For axial it will be 2p divided by 4 pi epsilon naught r cube. 2p divided by 4 pi epsilon naught r cube. So it is twice that of the equatorial, but sign is positive provided r is very much greater than e. Okay. So these are the two important derivations that you have to remember. So equatorial one and the axial one along any line. So it is a simplification which we have. So you have to consider the total or the net electric field at the required point and then substitute the corresponding equations carefully and then find out the final value. Okay. I hope today's class is clear with. So further we will go with the Gauss law and the distribution of electric charges and the electric field. Thank you for watching. Thank you.